Hello everyone, my name is Yunus Kucuk. I am a PhD student in Binghamton University. Today I will be talking about our research paper, Deceiving Portable Executable Malware Classifiers into Targeted Misclassification with practical adversarial examples. I hope you enjoyed it and thank you in advance for listening to my presentation. First, I will briefly talk about our motivation for this research. Second, I will explain our methods for deceiving malware classifiers. Then, very shortly, I will show how we test the functionality of the malware examples we generate. We will see the evaluation of the results, and I will conclude the presentation. Malware is a serious threat, and it affects people, businesses, and governments every day. Malware threats are not only increasing in numbers, but also they are evolving in time. This figure is taken from AV Test Research Institute. The figure shows that how many new malware specimens are observed every month for the last 2 years. Only in July, until July 20th, 6.95 million new malware samples have been emerged. Machine learning has been widely used in detection and classification of malware, and it has shown great success. However, the increasing use of machine learning in malware defense has raised concerns about their robustness in adversarial environments. Recent studies show that automated malware classification is vulnerable against adversarial attacks. Previous studies focus on development of efficient algorithms for finding adversarial examples instead of creation of real adversarial samples. In this research, we address these issues. We have studied on multi-class malware classifiers performing targeted attacks using functional adversarial samples. For this study, we extracted static and dynamic analysis features and built 3 different types of multi-class classifiers. The first one is based on frequencies of opcodes in the disassembled malware code, opcode classifier. The second one is the list of API functions imported by each portable executable sample, API classifier. And the third one is the list of system calls observed in dynamic execution, system call classifier. We carefully manipulate these features to achieve targeted misclassification while preserving their maliciousness and their functionality. So, how we manipulate opcode features? This figure is a simple depiction of LLVM toolchain. LLVM integrates a compiler and other tools in its infrastructure. In the front end, it takes an input source code and converts it into LLVM intermediate representation code, IR. LLVM optimizer allows us to optimize this IR code. In the backend, the executable code is generated. We would like to achieve our goal, manipulating the executable code by performing transformations in the IR level. Optimizing the IR level code is easier than manipulating the executable code directly. Here I will show how we perform the transformation. We implemented a bogus control flow obfuscation in the IR level. Simply, a basic block is a code block with no jump or branch instruction. We obfuscate IR level basic blocks by carefully inserting fake ones. The obfuscation method first clones a basic block and it adds the cloned basic block to the control flow just after the original one. The obfuscation method uses opaque predicates for always true conditions. The fake basic block will reside in the executable code but will never be executed. We define an optimization problem, and if we find an optimal solution to this problem, we can generate an adversarial malware sample P prime using a base sample P. For each cloned basic block in the IR level, we calculate the change in the current value of every opcode, and we generate a delta vector. Next, we determine how many times each basic block should be transformed, in other words, obfuscated. Dot product vectors of M and delta vectors gives the total change in the current value of opcode features. One problem we encountered in the basic block obfuscation is consistency. For our method, cloning a basic block should lead to linear changes on the counts of opcode affected. However, this is not always true for all basic blocks. For example, in this table, we compare the count value of move opcode when we clone the basic block index 3 and the basic block index 86. For basic block 86, after the first iteration, the increase of the move opcode in the sample is always 5. So we expect the difference in the count of move opcode between iteration 5 and iteration 100 should be 475. However, it is 478. Therefore, it is not a consistent basic block. We filter out these inconsistent basic blocks from our experiment and use only the consistent ones. Our second objective is manipulating API call features to deceive API call classifier. API function names provide important information about malware behavior. API obfuscation techniques have been widely used to cause confusion. In a portable executable sample, API functions appear in the import address table. For our purpose, any API obfuscation technique that prevents the API function names from appearing in the import address table would be enough. For the API obfuscation, we adapt this technique. First, we load dynamic libraries using load library function. Then, we replace every drag call to the API functions in the source code, extracting function handles using getProcAddress function. We also obfuscate the DLL name strings and API function name strings with the base 64 encoding scheme. These techniques are sufficient to fool the IDA-Pro tool used for static analysis. We define a new optimization problem for deceiving API call classifier. Each element in the obfuscation vector M takes only binary values. Every value indicates whether the corresponding API function should be obfuscated or not. Here, the feature vector of the obfuscated sample becomes the element-wise multiplication of the base sample feature vector and M. Our third objective is manipulating system calls. System calls are observed through dynamic analysis in the execution of malware. We cannot directly add system calls in the source code. Instead, we focus on API calls. We insert dummy API functions in the execution path. For each these API calls, we monitor the difference in the system calls invoked by the malware. We observe the changes in the count of system calls, and we create the delta vector. Here, there are some limitations. Invoked system calls should not break the execution path, otherwise it changes the behavior of malware. For deceiving system call classifier, we define this optimization problem similar to previous definitions. Here, M indicates the number of times each API should be added to the execution path. So far, we have seen our methods for manipulating malware samples. Also, we defined optimization problems for generating adversarial examples. Now, we should find optimal solutions to those problems. After testing a few optimization techniques, we choose the genetic algorithm. In the genetic algorithm, we first initialize a random population. The population consists of individuals of vector M. For each individual M in the population, we use it to modify the original sample based on the optimization problems. The modified synthetic sample is fed to the malware classifier to check whether it achieves targeted misclassification. If it passes the targeted misclassification test, we create the corresponding real sample through compilation and then test its functionality. If the malware sample works as expected, the genetic algorithm returns the sample. If none of the sample passes the tests and the algorithm does not satisfy the stopping criteria, fitness scores are calculated for each modified sample. We use 3 different metrics to calculate the distance between a synthetic sample and an anchor sample. We choose the individuals with the highest fitness scores and perform selection, mutation, and crossover operations. New individuals generates a new population. The algorithm continues these operations until it reaches the maximum generation. Here, our algorithm relies on an anchor to achieve targeted misclassification. Anchor is a sample from the target family. We assume that the attacker has access to a set of samples from the target family. We try to minimize the distance between the anchor and the modified samples. If the current anchor fails to find a practical adversarial example, we choose another anchor and rerun the genetic algorithm. For functionality testing, we perform dynamic analysis. We run the sample in a sandbox and observe the behavior. We create a command and control server and simulate the communication between the malware sample and the server through a merge channel. We send these commands to the infected machine. If the bot machine's responses to these commands are the same as expected, we say the malware sample is functional. For evaluation, we worked on a dataset with more than 25,000 malware samples and 519 benign samples. We trained the classifiers with random forest and we achieved high F1 scores. We preferred working on a malware sample that belongs to one of the output families of the classifiers. We used an Rbot malware source code publicly available. We add this sample to the training dataset so the classifier can correctly classify it into the correct family. We used Microsoft Visual Studio Compiler and LLVM compiler for compilation. To produce the executables, we used Microsoft Visual Studio Linker. We performed analysis in Windows 7 virtual machines. Our results for deceiving the opcode malware classifier into targeted misclassification are summarized in this table. We have mutated the original Rbot sample and we achieved targeted misclassification successfully for 9 target families with a successful rate of 75%. For 3 target families, we could not find a practical sample even we use all the available malware samples. The execution time spent on each anchor exceeds the validation time. The execution time varies, but if the genetic algorithm fails to find any adversarial sample, its execution time takes approximately 24 hours. One side effect of cloning basic blocks is that it increases the malware size dramatically. For the API call classifier, we successfully deceive it into targeted misclassification for 10 families, with the exception of 2 families. The execution time spent by the genetic algorithm is short, varying from a few seconds to 3 minutes. In the successful targets, only 1 anchor sample is enough for targeted misclassification. In this obfuscation, malware sizes are slightly larger than the base sample. We have seen the highest success rate in this, deceiving the system call classifier. We achieved targeted misclassification successfully for 11 target families. For the majority of these families, only a few anchor samples are needed to find a successful adversarial malware sample. The execution time for 1 anchor takes approximately 2 hours at most. As it is in the API call classifier, the adversarial samples do not have large file sizes. In this work, we studied new threats for deceiving multi-class portable executable malware classifiers. We built 3 classifiers using different malware features: opcode, API call, and system call. We deceived the 3 classifiers into targeted misclassification with high successful rates. We generated functionality-validated adversarial examples. We showed that genetic algorithm is instrumental in finding successful adversarial examples against malware classifiers. Thank you.